Hello, in this series of videos, we will set up an internal flooding scenario. The scene involves 3 rooms. The top room where the pipe break originates, the stairwell room where the water leaks under the door, and then onto the bottom floor. This video is part 1 of the series, and we will build up the follow-up videos on this. In part 1, we will learn how to couple a static model based on Torricelli's law in the top room to create particles which are used to simulate the hydrodynamic conditions in the stairwell room. First, let's download all the geometry used in this simulation from the website indicated. I will pause here for a few seconds for you to make a note of this, or you can click on the link. Okay, let's go ahead. Let's now create some rigid geometry objects for boundaries in Neutrino. You can create it from the Edit menu to the Rigid and Rigid Custom, or you can use it from the Scene Builder, and we'll show that later. First, create the geometry for the top room. Let's call it top room floor. And the mesh file path, you can point to the file called rbccw116 floor, and which is an STL file. Now, the geometry we loaded was modeled in a different CAD package, which had probably z-axis as up direction. Since Neutrino expects y as an up, we have to swap the y and z-axis. And also the model was probably modeled in a different units, so we get the appropriate scale. In this case, it happens to be 0.1, so we enter that as the scale. And then there, the object is imported. Okay, now let's change the color of the object from blue to white. And let's open the Scene Builder. From now, we will create objects in the Scene Builder, which is relatively a little bit simpler to create. Let's now import the HPCI floor model, which is the bottom floor, and repeat the same process. Swap the y and z axis and set the scale to 0.1. Now, I have to tell you about this option called volume sampling. Neutrino samples the boundary with particles, and the default method may not be good enough in this case. So let's turn on volume sampling in order to get a better sampling of the boundaries. Now, let's import the stairwell model and call it bottom room floor. Now enter the model, which is HPCI stairwell room stair.stl. Once again, in this case, we have to swap the y and z axis and set the scale to 0.1 to match the units in Neutrino, so everything's consistent. We have to turn on the volume sampling again, and we have to turn on volume sampling for all the rigid bodies which access boundaries in the scene. Okay, now we have imported a few objects, and we seem to have good handle on things. So let's now inspect the stairs. As we move close to the stairs and the top floor, we start to notice a slight bit of a gap. And that is probably because of modeling discrepancies or how it's imported. So let's just move these stairwells closer to the floor, and so that there is no significant gap. So it's a bit of an offset in the x and y direction, I think. Now let's create another rigid object, which is basically for the top walls. First, let's rename the current stairs, which is the earlier rigid custom 3. Now we've created a new object, and then we call it the room wall for the top floor. Let's import the STL file, which is rbccw outerwalls.stl. And we repeat the same process, swap YZ axis, turn on volume sampling, and change the scale to 0.1, and we get the things in place. Now let's turn on the display of the top wall to wireframe, and you can see how the toolbar on the left is used for changing the different display options for each of the geometry import. And create another rigid custom, and this time it's for the bottom wall, and import the geometry, which is hpci outer wall.stl. Repeat the same process, swap YZ, change the scale to 0.1 and turn on volume sampling, and you will see that the bottom wall falls in place. Once again, we can change the display to wireframe or keep it as it is, as you please, or we could even hide this geometry. Now let's go ahead and make sure the volume sampling is on first, and go back and forth and check to see the other geometry to see if everything is set up correctly in terms of volume sampling. Let's create another rigid custom, and this is probably going to be our final geometry. It's called a door, and let's import the door. The door is RBCC W116 door. Let's change the scale to 0.1 on all directions. And you notice that the door is a little bit offset. Once again, this could be because of the modeling differences or the units, or could be some errors in the model itself. So let's position the door correctly, since the model had an error in the position. So we'll just shift it 0.5 units or so in the X or the Z direction. I think it's the Z direction in this case, and kind of slowly eyeball it so that it comes into place. And there you go. That's the entire model. Turn on the volume sampling again. I think we had the other options already on, otherwise it wouldn't be in the right place. Now let's adjust the opacity of the bottom floor wall, and in order for this opacity to work, we need to change some options in the OpenGL rendering, and go to the OpenGL inside the system inspector and change the transparency mode to linked list transparency, and we can do the same for the top floor wall itself. This is just a visualization thing, and you can just continue to do your work. If you don't feel like doing this, go ahead, but it just creates a nicer looking image of the entire scene. Now finally, we can move on to setting up the solver and the emission system. First, let's create a source called a Torricelli source. We will use the Torricelli source to emulate the water accumulation in the top room, and we are using Bernoulli equations for the top room, which is a static model, and we will use it to emulate or simulate particles on the other side of the room. So we can create 3D fluid on the stairwell side of the room, and it will be just a visualization and a display, and just static equations for the top room on the other side of the door. We need to position this Torricelli emitter right behind the door so that we can emulate the flow behind the door. We have to adjust the scale so that it is roughly about the size of the gap underneath the door, and the size of it will change as water accumulates, but for now let's start off like this. Let's place it right behind the door. The Torricelli emitter has got a few different options, and we'll go over these options one by one. The most important option is the inflow rate. So we need to set this inflow rate to the pipe breaks flow rate. So the pipe breaks flow rate is a known quantity, because we can determine that from this area of the pipe break, and so we can determine the inflow. And also the accumulation area is the area of the top floor, and in this case it's about 281.5 meters, and the accumulation floor height is the height of the bottom of the accumulation from ground level, and in this case happens to be about 38 or so meters. And let's put that in there, And now let's create the solver itself, which is the Neutrino II-SPH solver. And once we have that in there, let's adjust the resolution. In this case, the default might be just good enough. It's 0.2 is the interaction radius, and half of it will be the particle rest distance. So let's go ahead with this, and I think we are in good shape to go ahead and run the simulation. And now we are almost there. Let's just examine it. You can see the Torricelli source is displaying a big rectangular or a square area, and that kind of determines the area which we just input. As you get accumulation, as you simulate, this area will grow. We are now hiding the top wall geometry so that we can see things a bit clearer. This is just a visual thing. It's still going to be an active boundary and participate in the simulation as a boundary, but we're just not seeing it. And we're turning on the Torricelli's display, and finally arming the simulation and starting the simulation. And as it proceeds, you will find that slowly, as the accumulation builds up, and you see there's a small build up, and there's a green lines kind of move upwards as the flow rate makes the accumulation in the top floor increase. And there is a kind of a leak under the door, and then there you see which is the particles which are flowing through as a result of coupling the Torricelli source. And the reason that these particles are just one layer thick is because that's how high we scaled up the Torricelli source right from the beginning, because that is the size of the gap under the door. And if that gap is lesser than the particle size, then the flow will be approximately roughly compensated for that. So this lets us have particle size bigger than what the gap is under the door. So as you can see, the simulation proceeds. We have a static flow on the top room. We don't even see the particles because that's all internal to the simulation. It's just a hydrostatic condition. But we do see the hydrodynamic effect of it as it goes underneath the door and builds up the accumulation, and it goes into the stairwell. And those are the fluid particles entering. So in the next video, we'll examine how to set up particle systems on both sides of the door and enable particles to transport under the door even though the door gap might be smaller than the particle size. And this will involve a couple system of killers, emitters to get this working. So please get ready, and we can move on to the next tutorial. Thank you.